Actually, there was supposed to be one more talk about that topic, but it's been cancelled. And actually, my goal is to finish the conference as soon as possible and go to the discussion. So I try to finish this one in 20 minutes. My talk, I'm going to mostly talk about the long. So I'm talking about the parabolic equations. So we have a time variable, and my concern is the long-time asymptotics of the solutions. So that is the topic. So for example, okay, consider some equation, parabolic equation, or it can be even a hyperbolic equation, and in this kind of form, and with the initial value. And my talk is considered for only the L1 solutions only. Then if you want to consider the asymptotic behavior of solutions of this kind of equation, then I think the basic question is, what is the mechanism that gives the asymptotic behavior? So what are the key players that decide the long-time asymptotics of this kind of problem? So that's I think the main question of the problem. And actually, even if I write it equation in this form, many people consider this kind of equation, for example, conservation law. Now, this is heat equation, and this is Berger's equation. This one is force medium equation. This is Laplace. Okay, so many of the equations people consider is always written in this way. Then, what are the main players and how to control the long-term asymptotics? The story of my talk is this. Then, first, let's formulate our question. Okay. Then let U and V be two solutions with these two initial values. And okay, then can you find the optimal contraction order gamma that can given by in this form? We may consider what the LP norm, but for simplicity, I think that but the error norm is the most important one in this context. Then what is the contraction order? And to get the contraction order, we need some suitable conditions. And what are the conditions for this initial values? And if you want to increase this contraction order, that means in some sense you want to control asymptotic behavior of two solutions, then what should we do? Or then what is the main factors that decide this kind of contraction order? So these kind of things are my questions. Sometimes if people want to say, instead of the word contraction, people use convergence. But for the previous problem, basically the error solutions are basically decays to zero. So if you want convergence, there should be something, right? Then, for example, if you consider the heat equation, and then these are the similarity variables. If you transform the heat equation, for example, then you get this one. And now this one has a non-trivial steady state. Then, okay, if in this sense, people still say that the convergence rather than contraction. Then, so this equation has this steady state, and this one is basically the Gaussian. If you use the original variable as ante, then this one is the heat column. But still, I prefer to use the contraction because in similarity variables, this one is a steady state. But if you return to the original variable, then still this one is a time evolving solution. So I would rather use the word contraction order rather than convergence order. And this kind of long-term asymptotics, and many people try to obtain the optimal convergence order for T large. And there are many papers and many people who work on that. But clearly, if the total mass of these two are not identical, what all you can expect is not the not the contraction, but you may expect only order 1 because basically it is a conservation law and mass is preserved. And if you start with a different mass, then error norm cannot go to 0 in time. So, and in particular for the porous medium equations in this form, and this is the regime for the conservative mass, then many people studied the asymptotic behavior, and many people obtained many kinds of contraction order. And so suppose we have the same total mass, and then if we just consider very general initial value in L1 space only, then all you can obtain is just the contraction or the little o, but there is no contraction order gamma in general, so gamma cannot be obtained. So what people consider is that give some extra conditions for the initial value and obtain some convergence or some contraction order gamma. And in the literature we can find this kind of contraction order, and this one is this order is well known for porous medium case, and this one is somehow similarity scale. For example, if you consider a heat equation, then m equal 1. M equal 1, that is the square root of t. So 1 over square root of t. So this one is the well-known similarity order. And to obtain this one, first we need this kind of agreement of the total mass, and we need extra assumption that initial values are decay fast for x large. So we need some assumptions on this initial value for x large. Then people obtain this kind of convergence order. And another typical approach to obtain the convergence order is using the monotonicity of the entropy, and using the method when people may obtain this convergence order. And the assumption for the initial values are they have the same total mass and same center of mass, and the second moment is phi. So under this kind of assumptions, people obtain this kind of convergence order. And there is another different kind of convergence order, which is t to the minus 1. And here, center of mass is usually center of mass and total mass, they agree to each other initially. And also, some extra condition is required for the initial values for x large. For example, if we consider porous medium equation for m bigger than 1, then the initial value should then the fundamental solutions has compactly supported for all time. Then, for example, for that case, it is required that these two initial values have a compactly support. Then, and so with the compactly supported initial values U0 and V0, if these conditions satisfied, then people may obtain this kind of conversion. So, obtaining this kind of order has been done by many people for the porous medium equation case. And what I want to talk about is, okay, I want to go a little bit further. And for the heat equation case, there are very good properties. So here, let's just consider the one-dimensional case. And if we can do the one-dimensional case for this one, you can easily extend to the multi-dimensional case also. This is a heat equation. What's the moment of the solution? Moment of the solution is just this, multiply x to the kth and to the integral. Then we call this one kth order moment. Okay. Now, if it's U is a solution of heat equation, you can easily check the derivative in time of the moment is given by. So now U is the solution of heat equation. Replace this and use the integration by part twice. Then you get this. So this one says the derivative of the moment is given by the moment of the previous orders. And if you use this relation, you can find this relation. And this relation says that the moment is completely decided by the initial moment. So if you have two initial values with the same moment up to certain order, up to certain order, then those two solutions always have the same moment up to certain order, because this one is completely decided by the initial moment. And if you see this moment, so we know that if you put the solution of the heat equation, then this one is defined for t bigger than 0. So you cannot go backward. You have to go always forward. But if you see the moment, if you plug in some negative numbers, then all of these things are well defined. So somehow you can always think the moment in the negative time. It's always. And I use the backward. So I call the moment for negative time or backward moment, and that one is sometimes very useful to use. So if two initial solutions have the same moment of this order, then they always have the same moment of that order. And using this relation, you can obtain a contraction order of this. Okay. So if you can control the moment up to order n-1, then you have this conversion. And we need one extra condition to obtain this. That one is okay. The moments agrees up to order n-1, and the nth order moments, they are finite. Then you can obtain this conversion. So here we can see that deciding this contraction order, if you control the moment that you place in the role, and here square root of t also involves, that one is exactly the similarity scale of the solution. So these two things plays the main. Then how to control the moment? So there are many ways to control the moment. So select U be my original solution, and I want to approximate, or I want to control the solution using V. Then if you set V in this way, then this one has the moment of this one. So what is this? E is the heating column. Now derivatives of heating column. This one is a kind of a linear combination of these derivative of heating columns. And if you plug in the moment of the solution U at the initial time, and you made this summation, then you can easily check the initial moment of this one is the same as the initial moment of U. Okay. So that's one way to control the moment. However, this one is not so good. Not so good because you are using the derivatives of the heat column. And if you differentiate again and again, for example, when t equals 0, this one is the delta measure. If you differentiate the delta measure many times, it becomes very bad. And so okay, but is there a better way to approximate or control the moment? Then somehow we may consider a linear combination of the heat columns placed at point Ci with weight rho I, and decide the Ci and rho I. Then for t equals 0, then the initial value somehow corresponding to this. Then check the moment. The moment is simply given this. Then find rho i's Ci's that matches that matches this initial moment of the original solution u. And here we have two and freedom of choices, then use them and then solve this somehow. Then solving this one is exactly called the moment problem. So many people do the moment problem. So probably the people who do this kind of heat equation or parabolic equations are not familiar with those moment problem people. But they exactly that theory can help us to control this moment. So there are other ways. Okay, so even if we use this one initially this one is a lot better than this. But this one is still bad because there's delta measures. So somehow we use T. Then this one has more regularity, and there is better way to control this one using the backward moments. But I'm not going to go through. I'm not going to do that. Now here there are more. But we can do this. And then instead of using one time T naught, use various time of TIs and make some approximation or control the moment using this one. Okay, if we can do this one, that is the finest one, but we do not know how to control the moment using this one. No, I have no idea. But this one is doable. This one is, we did this one and we used this one extra parameter. Then we may improve the initial approximation a lot. But this one, ultimate goal, but I don't know. Now the Burgers. Okay, let's consider the Burgers equation. This one is a Burgers equation. Now initially, suppose that initially u and v at the same moment of some certain order. Then do we have then these two solutions have the same moment for all time t? If we have the same moment initially, the answer is no. There is a big difference between linear heat equation and nonlinear Burgers equation. So even if we can match initially, even if we can match the moment initially, all we can obtain is this kind of contraction. So even if we match all the moments, okay, that doesn't matter. Only we can this one. Then what should we do? What we have to do is, okay, instead of controlling the moment of the solution of the Burgers equation, use the Korff transformation. And the Korff transformation, then this one is a solution of heat equation. Now match the moment for this one basically. Okay. Then take the inverse transformation, inverse Korff transformation. Now double that. Now this one is a solution of the Burgers equation. Okay, then we can show that the solution of Burgers equation and the Wn obtained in this way has this property. So the difference and this is not exactly the moment. This is not exactly the case of the moment. So the difference of the case of the moment is just a simple integration. But here we take a known, L1 known. So this one is different. But it seems that this kind of thing is the main thing to compute the contraction order. And you can see this. So then here, for example, our most interest is that when k equals 0, if k equals 0, we can obtain this convergence order. So what happened here? Originally, if you try to match the initial moment of the solution, that does not give you good asymptotic behavior. The reason is, for the asymptotic behavior, you want to see the things for t very large, right? So initial agreement does not matter. So the important thing is asymptotic agreement. And if you control the moment after the Korff transformation and go back to the Burgers equation case, then this one and the solution mu does not have does not have the agreement of the moment initial time. But somehow this cohort transformation makes this the moment at t infinity agrees. So this is that argument. Okay. So from the study of the Burger's equation, what I realized is that the important thing is that so here still square root of t. This square root of t is also the similarity scale of the Burger's equation, which is same as the heat equation. Now the number of moment control occurs here. Now, if you consider this force medium equation, so what will happen? Force medium equation, then the fundamental solution of the force medium equation is called the Parabolic solution. That one is given explicitly in this way. Now, the similarity variable Psi is x t to the minus alpha. This alpha is this one. And if you consider the different one, this is T Laplacian equation, then still this one has a fundamental solution in displaced form, and the order alpha is this. Sometimes we want to consider an equation that goes with a convection. Now, force medium type diffusion, the Laplacian type diffusion all together. Then we know that this one has no similarity value. But there is not similarity scale, but there is a scale that decides the long time behavior. For example, in this case, 1 over Q is the similarity scale of this convection. This one is the similarity scale for this T Laplacian. This one is for the force medium equation. Now, if you take the maximum of this one, somehow this one gives the asymptotic scale of this one. So even if the problem has no similarity structure, you can many cases you can find some scale. We may call this one asymptotic scale, such that this one converges to L1 function. So after this kind of scale, so in this problem, if you take alpha as a maximum of this, then the solution after this rescaling converges to some L1 function. So we call this alpha as a similar asymptotic scale. So for more general solution problems, this one plays the key role deciding asymptotic behavior. Okay. So for example, the UMVP solution of this one, or one-dimensional case in this kind of form. And now, so the Burger's case is a completed theory. But now this one is just a formal statement. Let T to the alpha bit asymptotic scale of the problem, and let E be their difference. Now, suppose that the nth order moment in this sense is of order 1 for T large. So somehow we have already controlled the moment of these two, and the difference satisfies this kind of relation. So nth order moment somehow bounded in for T large. Then somehow this one gives that the lower the moment should converge to zero with certain order. But if we have this one, then we can obtain some convergence order. That alpha is the asymptotic scale. Now let's take just arbitrary beta, and later I want to say that this beta should be alpha. So then let's take beta arbitrarily, and then after the change of variable, this moment is written in this way. And suppose that if you can find some constant c, little constant c, bigger one c, so positive and independent of time, that satisfies this relation. Okay, suppose we can find the constant, this one. Then claim is we can obtain the optimal convergence. And if this one is obtained, then you can easily check that this beta should be alpha. For example, I'm a little confused. If beta is bigger than alpha, then what happens? Okay, so if you have alpha here, then this one converges to f, to some L1 function. But if beta is bigger than alpha, then this one. If beta is bigger than now I remember. If beta is bigger than alpha, clearly this thing behaves like a delta measure, so it's concentrated, and this one is same. So if you compute this one, that one should be 0. Here you have y to the nth power. That is delta measure, something like a delta measure. Then this becomes 0. So you cannot obtain this. Similarly, you can also, if beta is less than alpha, you cannot obtain the constant that satisfies this one similarly. So this similarity scale or asymptotic scale should be placed. If you have that, then there exists the C star between these two constants that satisfies this, and then you can easily check that this, after the change of variables, you can easily check that this one is the order 1. That means it's L1 mode difference has order multiplicity to the minus n alpha. So n is the number of control of moment, and then alpha is the asymptotic scale. And for the PDE equation case, for the Parabolic equation case, we know how to control the moment. General case, we do not know. However, here what I'm saying is if you can't control the moment, you obtain this higher order asymptotics. That depends on the number of moments, and that depends on the asymptotic scale of the solution. Okay, so this one is the rephrasing. Here I rephrased the argument a little bit formally.